The tech industry routinely makes a basic categorization error. We point to a prompt window generating fast, complex text and call it an autonomous agent. But single-call request and response models are entirely stateless. Large language models, systems trained to predict the next word in a sequence based on massive text datasets, lack environmental embeddedness and memory. They execute a command and immediately forget it happened. To build a functional metaverse, the AI Metaverse Working Group, or AIMWG, established a strict official standard. Under this framework, true agency has absolutely nothing to do with whether a system uses machine learning. It relies entirely on a concept called temporal continuity. To qualify as an autonomous agent, an entity must maintain an internal state that persists across multiple interactions. Its history has to actively influence its future behavior. Treating stateless tools as autonomous entities creates catastrophic architectural flaws when attempting to build persistent spatial computing environments. This diagram shows an agent's perception action loop. The agent continuously samples its environment. It processes this data, exercises discretionary action selection, and pushes an action that alters the environment. The changed environment alters the next sensory data. This creates a continuous, unbroken circuit. The AIMWG standard defines this cycle as structural coupling. There is an ongoing dependency between the agent's internal state and external reality. Temporal closure grants the agent ontological presence. The entity dwells within the metaverse as a persistent inhabitant of the simulation. This diagram shows the engineering requirements to build a fully compliant agent. First is the sensory interface layer, which requires specific input channels to parse raw environmental data, filter noise, and determine relevant information. Second, we install a state management system. This maintains working context and stores long-term memory across perception cycles. Third is the motivational structure, providing built-in drives, distinct goals, and utility functions mapping preference orderings. Fourth, the action selection mechanism combines reactive and deliberative choices, resolving conflicts between competing actions. Finally, feedback processing evaluates the outcome, closing the loop back into the state management system and triggering behavioral adaptation. Lacking even one of these 5 modules reduces an entity to a scripted animation or a direct control proxy. It fails the standard. This diagram illustrates how the completed internal architecture integrates with the network. Information enters through perception flows, continuously ingesting authoritative world states from game servers and raw user signals from local clients. Information exits through action flows, pushing content modifications back into the environment. Surrounding this is the control flow, dictating the overarching authority with the power to start, suspend, or constrain the agent's lifecycle. These strict flow definitions ensure autonomous logic does not overwrite authoritative server states, which would destabilize the entire virtual ecosystem. This diagram highlights an immediate failure point for pure virtual reality agents. They cannot process physical boundaries. To solve this, the standard enforces the principle of physical-virtual continuity. An augmented or mixed reality agent must simultaneously reason across live physical sensor data and synthetic virtual assets. We add a spatial computing layer to handle SLAM, tracking the agent's exact location within a physical room. Next, a reality compositor manages lighting, physics, and occlusion, so virtual and real-world objects interact convincingly without visual conflict. An agent can only manifest safely in your living room if its architecture precisely synchronizes spatial understanding across both realities at once. This mixed reality perception introduces a severe risk. The agent is actively ingesting live camera feeds and mapping the layout of private physical spaces. To mitigate this, the standard mandates a hardware-level privacy manager. This subsystem enforces strict data minimization and ensures that visual processing happens locally on the device, rather than being transmitted to cloud servers. Alongside privacy, a safety monitor tracks physical hazards. It actively prevents the virtual agent from encouraging dangerous real-world movements, like stepping into a street or tripping over furniture. The architecture defines strict escalation triggers. These are specific environmental conditions, like a physical safety event or a privacy boundary violation, that immediately force the autonomous agent to suspend operations and yield control back to human oversight. Bounded authority represents the legal and ethical prerequisite for deploying spatial computing agents. These hard constraints are mandatory for any system operating in the physical world. We see this architecture at work in a practical application from the standard, an AR spatial task assistant guiding a user through an engine repair. As the user moves around the workbench, the agent's SLAM integration and computer vision pipeline continuously perceive the shifting physical orientation of the machinery. Computer vision is a processing field that allows systems to extract meaningful information and identify objects from live camera feeds. The agent relies on its spatial memory to recall previous interactions and errors linked to these exact physical coordinates across multiple work sessions. When the user reaches in to turn a wrench, the reality compositor recognizes the physical hand and dynamically adapts the virtual instructional overlays, ensuring the AR schematics are realistically occluded by the user's arm. This proves the definition of autonomy. It isn't playing a pre-rendered animation. It is a live, discretionary entity continuously calculating shifting physical constraints to achieve an internal goal. This defines the official AIMWG validation criteria. An autonomous agent must maintain state, perceive via sensors, execute independent actions, and achieve structural coupling. Mixed reality agents must also respect physical-virtual continuity and enforce strict privacy and safety envelopes. Simple chat interfaces and direct avatars fail these criteria. They act as tools or proxies, reliant on step-by-step human inputs rather than continuous temporal loops. The true measure of spatial autonomy is not raw computational intelligence. It is a system's ability to persistently, safely, and continuously intertwine its operations with the physical reality of the user.